right. So today we're gonna start the main chapters in this course. The mass spring mass system, or we can say mass spring systems. The goal is to derive the differential equation of spring mass system. Okay. So spring mass system is the, the equation is like this. So we're gonna derive it, but I just want to tell you what what it is. So first term, they represent the gravitational force. The second term from we obtain second term from the damping force, okay, or some kind of resistance force acting on the object. Third term from the spring force, because the spring mass system maybe, yeah, definitely spring force and gravitational force must be involved in the system. So third term is spring force, and then F of t on the right hand side represent the external force. So what that means? So think about the the spring is hang on the ceiling, and we attach the some object. It's called mat. We'll say mass m right here. Okay. And once you attach it, then the spring will be oscillating, right? The vibration will happen. So we're gonna observe it. In addition, we're gonna observe the displacement of the spring when we pull down the spring or some kind of external force acting on the mass, so that the spring will be elongated, and then finally vibrations like this. Okay. Or you just observe the experiment by installing the spring on the tube so that damping force is applied. Okay, think about the shock in a car. In order a car, you see the strut in the wheel in the car. There is the cylinder right here. Okay, so when car driving over bump, then the shock will have the oscillations, but that will decrease the oscillations because of the cylinder is moving along the tube, right? So there is a damping force is acting, or you just store the shock absorber in the door installed, and you can see the vibration will decrease because of that damping force. So anyway, so in a view of mathematics, we can describe the spring mass system as a second order linear ODE. Okay. So the second order ODE, linear ODE, can be classified as homogeneous and non-homogeneous. That homogeneous is not different, totally different from the homogeneous in what we learned in chapter 2. Okay. That homogeneous means the external force is zero. External force is defined by zero. Okay. And then non-homogeneous means that external force is not defined zero. Okay, so something non-zero function. And then in mechanics, we can classify the homogeneous as the unforced, undamped oscillator, and the unforced, damped oscillator. Unforced means that external force is zero. That's what we call it. This definition, this the equation as unforced, and then undamped means that the gamma is zero, which, or you can say no damping force is acting on the object. So unforced means that external force is zero. Undamped means that damping force is zero. No damping force. Okay. And then damped means that gamma y prime is the involved in the system. Thank you so much. I appreciate it. All right, so in the non-homogeneous, there are two systems in mechanics: forced undamped oscillator and the forced damped oscillator. So force means the external force is non-zero, as I told you. And then there's undamped, damped. Okay, so now we see the four cases in mechanics, where unforced, undamped, on force, damped, force, damped, and force on damp, undamped and damped, okay? And then on force damped, let's look at it. So yeah, definitely we want to find out solution for each cases, but the very in the 4.1 and 4.2, we want to focus on that case, unforced and damped oscillator. And then we're gonna it end up with three cases when you try to solve the equation of that case: over damped, under damped, critical damped. I mean, think about just imagine what happens when you just pull down the object in the cylinder and then release it. Then we see the spring will vibrate, right? In that case, it's underdamped. That underdamped means that the natural frequency of the spring is, I mean, the force caused by the spring is the bigger than the damping force. Because you can see that there is no damping force in this case, or some kind of damping force, even if a damping force is acting on the object, if the spring force is greater than damping force, then we'll see the vibrations. That's under damped. So beta is the rescaled the damping constant. That gamma actually the beta is gamma over 2m, something like that. Okay, so m is a mass and gamma is damping constant. And then the, omega 0 is natural frequency of the spring. So we'll talk about this later. But anyways, underdamped means that the spring force dominate the damping force, so that we see the vibration in the behavior of the spring. And the overdamped, it means that damping force dominate the spring, spring force, so that no oscillations. And the critical damped is a similar behavior as overdamped because beta equals natural frequency, so we see no vibrations. Okay, so we'll talk about this one at first, okay, and then we see, and then now we're gonna go to the non-homogeneous. Okay, not for solving non-homogeneous system, we need to study the method on determining the coefficient. Okay, so oops, sorry, give me a second. All right. So okay, so first let's just set the problems. Okay, so experiment. So spring is hang on the ceiling, okay? So and then let's say the K is the spring constant, or that K, or we can say represent the how strong the spring, or that represent property of the spring, okay? And then L is a natural length. Let me write it down. Oh, write it down by the way. So here, okay, L is the natural length of spring. Natural, just let me just say natural length. And then K is the spring constant. And then when we just attach the mass, the object, definitely the spring will be elongated. So L is a change in length. Sometimes we can denote L as delta Y. Here Y is the displacement of the spring from the natural length. Okay, delta Y, that's a change in length. Okay, so K, yeah, I just mentioned the K and L. Okay. KL here, and then here's a minus L here. I mean, first one, we need to set the direction of the position, because we're gonna talk about the force, right? Force has direction, so we have to set direction. Okay, which one is a positive direction, which is a negative direction, all for the for each for the force, right? So I'll set I'm gonna set that downward as a positive direction. So which means that every force the acting on the object pulling down will be considered as a positive value. Okay. So gravitational force must be positive. Okay, and then a spring force must be negative because the spring will what pull up the mass, right? So here's a negative, let's say negative L, okay, here, right? And then L here, and then this is 0. I set this 0 means that the that position is called the equilibrium position. ERIUM, okay, position. Which means that the spring force equal to the gravitational force. There is no movement. There is no movement at all. Yeah. So and then when we apply the external force where you just pull down or pull up the mass, then equilibrium position will be broken. So the mass will move, okay, up and down. So in this, that's the case C. Okay, so right here, that's the L changing length due to the mass, and then this one is actually y of t. That's the what we are interested. We want to find out y of t, equation for y of t, and then we want to figure out the y of t. Okay, so from L plus y of t. Okay, in this case, this is a delta y, sorry. In case C, y of t plus L, that's the delta y, which is a displacement of the mass from the natural length. Okay. So yeah, so yeah, as you can see, m is the mass of object. Let me just set all the letters, define all letters. Okay, so mass of the object. Okay, and then y of t, that's the displacement of the mass from its equilibrium position. Okay. So the delta t is what? Delta t is a changing length, which means the displacement of the mass from the natural length. This guy is displacement of the mass from the equilibrium. Okay. Mass from its equilibrium position. Okay. Equilibrium position. Okay, so our goal is to investigate y of t, which means the motion of mass caused by forces, gravitational force, spring force, external force, damping force. Okay. Okay, so let's just figure out each forces one by one. Okay. So first one, gravitational force. So that means the let's just say Fg. Okay, that means gravitational force. This is mg, right? Okay. Is it positive, negative? Positive mg or negative mg? What do you think? Positive, because we set the downward as positive, and then the direction of gravitational force is downward, right? So after this, you know what G means, right? G is acceleration due to gravity. M is just weight, right? Okay, so M is weight. Okay, and then G is the acceleration. With the gravity. Next one, spring force. So spring force denoted by F subscript S. That is the spring force is following the Hooke's law, right? So F is K times, this is K, okay? K, script K times delta Y. Because the spring force due to the elongated spring is proportional to delta Y. Let me write it here. So this one, the spring force is proportional to delta Y. Okay. Okay, is that minus or plus? Yeah, it's minus. Hopefully everyone got it. Minus should be. Okay. And then but delta Y depends on the case. Case B and case C, delta Y different, right? So let's figure out that for each cases. So case B, okay. So delta Y is L. So implies spring force must be minus K times L. The case B, case C, delta Y must be L plus Y of T. The F sub S is equal to minus K times L plus Y of T. Right? Okay, so this is equal to, this is equal to, yeah, okay. So minus K, yeah, I think that's it. Yeah, okay. So 1, 2, and 3. Let's see. Okay. I didn't want to mention this one first, but it's a net force. Eventually, we're gonna put every forces acting on the object on the net force. What does that mean? Net force is followed by Newton's second law of motion. F equals ma. F net is equal to m times a. What does that mean? The F net means the net force means the sum of all forces acting on the object. Okay, so that must be equal to m times a. That's Newton's second law of motion. Okay, so you know the right hand side. Okay, so see m times a. This is equal to m times y second derivative, isn't it? Because y represent displacement. A is acceleration. When you take a derivative twice of the displacement, we'll get the acceleration, right? So that's why ma is nothing but my second derivative. The right hand side, F net force is equal to what? The Fg, right? Gravitational force plus spring force plus and damping force. Let me say Fd, okay? F T, okay, and then plus external force. I didn't consider the sign, okay, plus minus sign of the force. Anyway, so net force must be this. From that, we're gonna get the equation for the displacement. It end up with the second, differential equation finally, but we'll see. So yeah, so this guy, this is net force. On the mass. Okay. All right, so the 4 3, and then yeah. So let's figure out the damping force and damping force and the external force. External force is just external force. It should be given, but okay, damping force. Sometimes resistive force. We call resistive force. Yep. So damping force is proportional to the velocity of the displacement. Fd is gamma, but this gamma times y prime of t. Okay. So here gamma is damping constant. Okay. All right. So then what do you think about the sign of damping force? Is it plus or minus? Damping force. Yeah, minus, right? Because the damping force against the what? Gravitational force, isn't it? But we figured out that the direction of the gravitational force is downward, which means a positive, and that some force against the gravitational force must be negative, right? The gravitational force is downward. It's set the positive. Okay, something force against that force must be negative, isn't it? So okay, so now gamma is damping. Okay, so 5, last one is the external force. Oh, oh, sorry. Yeah, just external force is just F of t. Okay, or you can say F sub EXTT, but let me just say capital, let me use capital letter F. Okay. Okay, now we're gonna combine everything. Okay. So combining all forces, 1 through 5. Come up with a difference equation. Okay. Then first one, that force is what? Is equal to mg, right? Gravitational force. And then spring force. Spring force is what? Spring force is negative, right? Negative k times, and then L plus y of t, isn't it? Okay, this is spring force. Fs, not gravitational force, sorry. And then this is the spring force, F sub s. And then damping force is negative gamma. Gamma and then y prime, right? So this is the Fd. And then finally, we got external force. So this is external force, Fext or Ft1. Okay. All right. So that must be equal to what? This must be equal to, that must be equal to what? M times A by the Newton's second law of motion, which is y Fmy dou prime, right? Okay. Okay. And so you know what? From here, what? Look at this. Mg minus k times L. Mg minus k times minus KL must be 0, right? You got it? Look at this. In a spring force, case B, Fs is equal to minus KL. But in case B, there is no movement of the object, which means that this one has equilibrium position state. Status of this situation is equilibrium, no movement at all, which means that the spring force must be equal to gravitational force. So what's the spring force? negative KL right here, that must be equal to M times G. Okay, so my mg, so here, since mg is equal to k times L, okay, so F net force is equal to minus, minus k times y, and then minus gamma and the y prime, and then plus n. Let me just keep writing parenthesis t, okay? So finally, we got this. Thus, my dou prime. So I'll move these two guys to the right-hand side, and then switch left and right. Okay, so we got this. My second derivative plus k plus gamma y prime plus k times y is equal to n. That's what we got this. This is a second order linear ODE. Yeah. So case one, I told you unforced in mechanics, unforced and undamped oscillator. I mean, as I told you, there are 4 cases in mechanics, depending on the spring force, external force and damping force. So unforced, and then unforced, then forced. Then forced, then undamped and damped. And then undamped oscillator. Okay. Oscillator and damped. So for this case, unforced, undamped, which means that no spring force, no external force, no damping force. So we got my dou prime, and then plus ky is equal to 0. Unforced, so no external force, damped, there is a damping force. So we got a plus and then gamma y prime plus k times y is equal to 0. Then forced, so there is the external force, and the undamped, no damping force. So my dou prime, that plus k times y is equal to f. And this is my dou prime plus gamma y prime plus k times y is equal to f. Okay. So. Okay. Okay. So then let's that's the just introduction of spring mass system. Okay. So next lecture, I'm gonna focus on the unforced and undamped oscillation problems to find out solutions.